You're scrolling Instagram on a Tuesday night, half asleep, and suddenly there's a face you don't recognize. Some person at a rooftop bar in Lisbon holding a cocktail. You've never met them. You don't follow them. They don't follow you. And yet the app has decided, with surprising confidence, that you might care. Tap the suggestion and Instagram whispers, followed by Maya. Maya is your college roommate, and the stranger, Maya's cousin's girlfriend. 3 hops away. You've never heard her name in your life, but the algorithm already filed you two in the same drawer. The question I want you to sit with is, how did it decide that drawer existed at all? Because somewhere in milliseconds, a tiny piece of math looked at a graph with billions of nodes and said, yeah, these two belong to the same neighborhood. That piece of math is older than Instagram, it's older than the internet, and it's hiding in your feed right now. Let's freeze this moment and zoom out. Imagine every Instagram user as a dot. 2 dots get a line between them if they follow each other, or message often, or got tagged in the same photo last weekend. Now multiply by 2 billion. That's the social graph. Inside this monstrous tangle there are clusters. Your high school friends, your coworkers, your climbing gym, your weird Twitter refugees turned Instagram mutuals. These clusters overlap, fray, merge, and every time you open the app, Instagram needs to answer a deceptively simple question again and again, fast. Is this stranger in any cluster that touches you? Not how close, just are you in some loose sense in the same connected blob? Because if yes, you're a candidate for a suggestion, a friend recommendation, a people you may know. If no, you might as well live on different planets. So the real puzzle isn't ranking, it's membership. And membership in a giant changing graph is its own special headache. Here's the naive way to answer, are these two people in the same blob? You start at user A, you do a breadth-first search, you walk every edge, you check if you ever stumble onto user B. For a graph the size of a small town, sure, fine. For a graph the size of Instagram, that's a tour of half the planet for one suggestion. And Instagram makes millions of these checks every second. So we need a structure that doesn't traverse, it just knows. Something that can answer same group in basically constant time, even as new friendships form every millisecond. This is the exact problem a computer scientist named Bernard Galler thought about in the 1960s, long before any social network existed. He was thinking about equivalence classes and compilers, but the shape of his answer is the shape Instagram needs today. It's called the union-find data structure, or disjoint set union, DSU for short. Here's the core idea, and it's almost embarrassingly simple. Every person points at one other person, their representative. Most people point at someone who points at someone else, forming little chains. At the top of each chain is a person who points at themselves. That self-pointer is the captain of the group. To check if 2 people are in the same group, you don't walk the friendship graph at all. You just follow each person's pointer up to their captain. Same captain, same group, different captain, different group. That's the find operation. To merge 2 groups, say you start dating someone and your friend circles collide, you find both captains and make one point at the other. One merge, done. That's union. The friendship edges themselves can stay as messy as they want. The DSU only cares about captains. Now, if you implemented this naively, the chains could get long and ugly. Imagine a union find where everyone points to the person who recruited them, and recruitment chains are 1,000 deep. Finding the captain takes 1,000 hops. We're back where we started. So 2 tricks turn DSU from neat idea into the fastest data structure most people have never heard of. Trick 1, union by rank. When you merge 2 groups, always attach the smaller tree under the bigger one's captain. This keeps trees short and bushy. Trick 2, path compression. Every time you walk up a chain to find a captain, you repoint everyone you pass directly at the captain. The next lookup is 1 hop. With both tricks combined, operations take, on average, what's called inverse Ackermann time, a function so slow-growing that for any input you'd encounter in this universe, the answer is essentially 4 pointer hops. To answer same group in a network of billions, let me make this concrete. Suppose Instagram has 5 people, you, Maya, Maya's cousin, the cousin's girlfriend, and a random guy in Sao Paulo. Initially, each person is their own captain, 5 tiny one-person islands. Then you follow Maya. Union. Now Maya is your captain, or your hers, doesn't matter. Same group. Maya already follows her cousin. Union, the cousin's tree gets attached. The cousin follows the girlfriend. Union again. Suddenly, all 4 of you share a captain. The Sao Paulo guy is still alone, pointing at himself. When Instagram's recommender asks, "Is the girlfriend reachable from you?" it doesn't walk the chain Maya, cousin, girlfriend. It checks your captain. It checks her captain. Match, boom. You're a candidate for the suggestion in 4-pointer reads. The friend of friend of friend got collapsed into one disjoint set. That's the title of the video. That's the trick. Now, I want to be careful here. Instagram doesn't publish its internal recommender code, and the real system is layered. Graph embeddings, neural ranking, engagement signals. Union Find isn't the only thing happening. But for the question of connectivity, are these 2 people in any plausible same blob? DSU and its cousins are textbook tools at this scale. They're used to maintain connected components in evolving graphs, to bucket users for candidate generation, to detect when 2 clusters merge after a viral event. The reason is brutal pragmatism. Instagram can't afford to traverse the graph on every scroll. It needs pre-computed, incrementally updated answers. And nothing updates faster than change 1 pointer. Once you see Union Find, you start seeing it everywhere. Take Google Photos. You upload 1,000 vacation pics. The app clusters faces. This looks like the same person across 47 photos. Each face starts as its own group. Pairwise similarity says, these 2 are the same person, probably. Union, 2 clusters merge, repeat across 1,000,000 pairs. At the end, every distinct person is a disjoint set, same algorithm. Or take your favorite multiplayer game's matchmaking. Players who've recently played together form groups when 2 groups queue, union. Or Kruskal's algorithm for building minimum spanning trees in road networks. DSU is the engine that decides whether adding a road would create a redundant loop or connect 2 separate towns. Or fraud detection. When a bank notices 2 accounts share a device, a phone number, and IP, union. Suddenly, a constellation of fake accounts collapses into one suspicious blob. There's a deeper pattern here, and it's the kind of thing that makes computer science feel like physics. Whenever you have a world where things can be declared equivalent, same person, same component, same fraud ring, same recommendation pool, and where these declarations only ever add, you rarely undeclare equivalence. Union Find is almost magically the right tool. The only add part matters. DSU is great at merging, terrible at splitting. If Instagram needed to handle unfollows by tearing groups apart, the data structure breaks down. You'd have to rebuild. But in practice, the social graph mostly grows. Friendships accumulate. Connections only get denser over time. So the algorithm fits the shape of human behavior. We don't really unknow people, we just stop interacting. Let's pause on the cost side because there's a real one. When connectivity is this cheap to check, it becomes economically irresistible to build products around it. Friend suggestions get more aggressive. Distant acquaintances surface. Your ex's new partner's coworker shows up in your people you may know. The same property that makes the algorithm efficient, collapsing many friendship hops into one membership check, also collapses the social distance we used to rely on for privacy. There's no technical hop count between you and a stranger anymore, only same captain or not. So the algorithm doesn't just decide what you see, it quietly redefines what near means in your social life. That's not a bug in Union Find. It's a consequence of using it on a graph that contains humans. Here's the aha moment I want to leave you with. We tend to imagine algorithms as smart, like the app is figuring something out about you. But Union Find isn't smart. It's almost stupidly mechanical. It points fingers at captains. It compresses chains. It answers same with a yes or no. The intelligence isn't in the algorithm. It's in the question we chose to ask it. And the question is, should these two humans be funneled into each other's attention? That question is a product decision, a business decision, a cultural decision. The algorithm just makes it cheap, and cheap questions get asked a billion times a day. So next time a stranger appears in your feed with followed by Maya underneath, you can picture it. Somewhere in a data center, two pointers got compared, 4 hops happened, 2 captains matched. You and the stranger were declared by silent fiat members of the same disjoint set. The math didn't decide you should care about her, it just decided you could. If you want to play with this yourself, UnionFind is maybe the most rewarding data structure to implement in an afternoon. 20 lines of code, 2 functions, try it on a tiny social graph of your own friends, sketch the edges, run the unions in your head, see how the captains shake out. You'll feel the same compression Instagram feels. And once you've felt it, you'll notice the pattern in face grouping, in fraud detection, in maze generation, in the way countries form alliances in your favorite strategy game. A 60-year-old idea about equivalence classes, born in a compiler paper, now silently arbitrating who shows up at the top of your screen. That's the strange beauty of algorithms. The small, elegant ones never really retire. They just find bigger graphs to live inside.